Hello. So the title of our talk today is Growing Bioterials to Minimize Material Transport. And we're going to talk about that in a couple different facets, including space travel and terrestrial travel. As you can see in the background there, what you're looking at is mycelium growing. And I'll briefly define bioterials as anything that uses the growth of an organism in its manufacture. A lot of time the term biomaterials get thrown around, but that usually refers to things used in the medical industry for anything that works well with biology. So that includes things like titanium and plastics. We're not talking about that. We're not talking about bio-based materials that are materials that are harvested, wood that's harvested from trees at the end of their life cycle. Biomaterial actually is something that uses the growth of organisms to make something. The first part of this is going to be space transport, and it currently costs a little over $10,000 to put 1 pound of material into low Earth orbit. Some estimates for getting a pound of material to the moon are about $100,000, and getting that same amount of weight to Mars about $1 million. So think of a can of Coke, basically, and do you want to pay $1 million for a can of Coke? That I think the delivery fee is a little bit too much on that. But when you think of things like building materials and all of the weight involved with buildings, that really takes things to a new level. If you have to pay $1 million for every pound of material you take to another planet, then you really need to think of different ways of doing that. Since this is biomimicry, we'll relate this to animals. You can either be NASA has this trade-off. You can either be like the turtle and you take your house with you, or you can be like the bird and build your house when you get to the destination you're going to. Those trade-offs are often, you can relate that to, on the left side there, you see the habitat unit, the HDU, and on the right, this would be a process, what they're calling in situ resource utilization, where basically you take material at the destination and you use that to make buildings. So in there you see a sketch of a robot that's basically 3D printing with lava, or the regolith that's melted, sintered, and 3D printed. We have a proposal. I'm working with Dr. Lynn Rothschild at NASA Ames for a proposal to actually do something middle of the road of that, where we're taking a small compacted bag, if you will, that is pre-seeded with biology, and then when it gets to destination, it's fed nutrients like water and carbon dioxide and nitrogen that allows autotrophic organisms to grow, and then we feed that to mycelium, which actually creates a strong composite of different materials. So you have the cellulosic matter of the autotrophs, and then you combine that with the chitin-rich material of the fungi, and you get a strong biocomposite, which I'm missing my sample, but we do have a sample around here somewhere that I'll be sure to pass around at some point. But we've made materials using, there it goes, it's passed around, using these composite materials. So it's basically using fungal mycelium to bind together organic biomass that becomes a composite with it too. This is a short video demonstrating how that might work. So you'd imagine this going before any crewed missions that go to Mars. There's a lander that puts this pre-seeded package there. It's met with a rover. The rover supplies things like water, nitrogen, and carbon dioxide that can all be sourced locally. All of the other nutrients are pre-packed into this container that is inflated first with gases and then filled with waters that allow the autotrophs to grow. And then you'll see here, we're looking at the cells of the interior of this. The water is filling the cavities. Now it's filling with the autotrophic organisms, which are cyanobacteria. It comes with its own light and heat and everything all within the membranes. But then once that algae is grown to make the filamentous colonies you see there, we release the mycelium to devour that and kind of create this composite. It's almost, it's very biomimetic in the sense that it's like a circulatory system supplying nutrients to different cells that create the interior of that. So it starts with an inflatable, which is obviously very light to pack and easy to go, but then it fills with a material that's more robust when it comes to radiation protection, insulation, and things like micrometeorites. This is just a cross-section through the building showing how the algal reactors might work to actually feed some of that nutrient source to different locations. We envision this as something that can possibly scrub carbon dioxide and human waste after the crude emissions arrive, that it becomes a filtering system. There's some other NASA NIACs that look at doing exactly that with the algal reactors. So yeah, we're talking about lifting mass. So if we start with a 13 ton building, and we expand that using things like water, carbon dioxide, nitrogen, as I mentioned, that starts to expand to over tenfold when we actually have this thing full of water, nutrient-filled water. But then at the end of it, when everything is dehydrated and compacted, it ends up being about a tenfold increase of growing materials. Now, it's just with this prepackaged project, but you could think of it as taking a factory and actually growing that. And then it's not too hard to imagine taking, grams of material and turning that into thousands of tons of material at destination. The detail of some of the cells. So we're using a technology called drop stitch technology, where there's polyurethane coated fabrics that are connected by strings, and then the material actually grows in between them, binding with those strings and creating a composite with the drop stitch material itself. Here's some microscopy of different samples where we've grown mycelium on the algae and other substrates, and you can see that the density of that depends on compaction and all the various factors, including substrate and species of mushroom, compaction, and baking. Here's another example of growing the fungus on the filamentous cyanobacteria and some samples that were created. So yesterday we heard from Dr. Dina Jwala that was talking about looking at this for radiation attenuation. That's some things that we're looking in together with him and researchers at Johns Hopkins. And there's a few different ways that we think that this material could be useful for that, including the radiotropism that he mentioned, creating melanin, which is a biochemical that the fungi can actually create. And there's also ways of bioaccumulating natural radiation attenuators like lead that can be found in different regoliths and things like that. So, compare something you grow on destination with something you might have to bring from Earth, like lead or polyethylene or things like that have a very high density to it. You're really saving a lot of money by growing that at destination, and having this bioperformative aspect to it actually increases the viability, because you could think of this as something that actually uses ionizing radiation as a resource, that is pretty much the main liability in space travel at this point. So here's a slide of some materials that were made as part of the MISSI program that Ali was talking about yesterday. And here's our samples actually on the ISS. And here are our samples outside the ISS. And if you see that white bar to the left there, at first I didn't understand what that is, but if I'm not mistaken, that's the Earth's atmosphere. So we're really up there in this one. A couple pictures of the materials pre-flight, and then here's a picture of the material pre-flight and or post-flight and control. And that's thanks to Dr. Kim DeGrow at Glenn Research Center, who's the head of the MISSI program. So we've started doing some tests on exactly what the material capabilities are. This is some XPS typography that was done by Andrew Trunick here at NASA Glenn. And this is a very preliminary study of the dosimeters that were put behind the materials that show the mean gray value difference of the material. So how much discoloration happened to those dosimeters that were behind the materials. And you can see from this chart that the PLA, the fungal derived mycelium, or fungal derived melanin, was actually the most consistent when it came to shielding. But PLA was already a good material for shielding, but then when it came to adding these other biochemicals, they really increased the ability for this, at least in this preliminary study, and we're doing quite a bit more now. So, mentioned that this could be used to grow the buildings, of course, but it's not just necessarily the buildings. As this video animated could include the furniture and fixtures and interior parts of the building could also be grown, and, that can even relate to things like vehicles or other things that are needed for missions, launch pads, things like that could be tucked away in certain ways that could be grown at destination. So here we see a bathroom, growing from nothing. The plumbing and electrical connections would have to already be there for this to be at least operational when you get to destination. But all of these components could be grown at destination, and you can actually have your can of Coke there already. But again, it's going to cost you $1 million to do that. So part two is terrestrial transportation. So, obviously taking things off planet, there's a huge burden there with the gravity well. And when we, were researching this, we wanted to make that correlation super evident that, okay, there's maybe not a cost implication as much with the transport, because we can get things from China extremely cheaply, but we assume that there's a carbon cost to that. And as we researched it, yes, there is a carbon cost to that. It's about 3% of the embodied carbon footprint of materials, but it's it's very small portion of it. But when you add that up to millions and millions of homes, obviously, you're talking real numbers like 2 million tons of carbon dioxide equivalency for the transport of materials alone in the U.S., just for single-family homes. So again, very small percentage, but it does add up over time. The real thing you can see there is the raw material extraction. That's about 84%. And so sourcing material from a circular economy appears to be the best way to do it, of course, but they both add up. And so we're going to talk about a couple projects today, but I'm going to mention 4 that we're working on. MycoHab, which Carolyn is going to talk about in a moment, uses the waste from what's called the encroacher bush in Namibia to create food and building materials. And we store carbon in the process. So the 3 things that come out of that are food, material, and carbon credit. The biocycler is one that we're working on here in Cleveland, where we actually take construction and demolition waste material and convert that into building materials, but not only recycling, but remediating some of that waste. So the building industry is famous for putting lots of poisons into our environment, and we can use that biology to actually clean that. EcoHab, you saw Thibaut talk about this earlier today, where we talked about the non-point pollution sources that end up in rivers and lakes, and I guess our livers too. But that things like the phosphates and nitrates that are put into fertilizers end up causing harmful algal blooms, and that material can actually be harvested and turned into building materials. And then I kind of alluded to it earlier, but what is the waste resource when we talk about taking something to Mars? Because obviously there's not acacia mellifera bush, there's not encroacher bush or houses to demolish there. But I kind of alluded to it. It's the ionizing radiation. So if we can actually use that as a resource to make material, if we can use that as a nutrient to power the growth of organisms, either naturally or synthetically, then we can make materials from what is currently a liability for space transport. As I mentioned, the transportation is one thing, but obviously carbon storage is a major thing. What's bigger than buildings? Besides the Earth, there's really nothing bigger than buildings. So this is a great place to store carbon. And you can calculate the carbon storage of buildings by taking the carbon drawdown, which is the removal of carbon dioxide from the growth of organisms. So all photosynthetic organisms obviously breathe carbon dioxide and put that into their biomass and store that away. But usually that gets re-released in some way, either by eating that, becoming our biomass, and then we breathe that back, or decaying and releasing those greenhouse gases back. But if you can take subtract the carbon emissions that involves making materials out of that, you get the net storage of that CO2, and you can store things for the life cycle of a building. and sometimes longer, depending on how the carbon is stored. The equation for figuring that out is very simple. You take the plant-based material, and you take the carbon within that, so the percentage carbon, the amount of carbon in the material, and you multiply that by 3.67, which is basically the ratio of carbon dioxide to carbon. So when they're converting the carbon dioxide into biomass, they are expelling the oxygen part of that, the O2 part of that. They keep the C, and that's basically how you get a carbon dioxide equivalent. Fun fact about carbon storage in building materials: if we were just to use the waste straw in the U.S. Farming industry, we could put those into building materials. We could offset all of the transportation emissions. So that's a kind of a 1-to-1 right there. And so we're currently using some projects that use straw bales as the building material for our buildings here in Shaker Heights, in Bath, Ohio. So we have a few projects that are going on like that. There's a lot of projects in Canada by an architect named Chris Magwood, and he's basically where that quote comes from. Writes a lot for the new carbon architecture and for tree hugger and things like that. You might have heard of him. But using straw, wood, and mycotexture, you're able to store carbon for long periods of time. And so with that, that brings us to our project MycoHab, and I'm going to introduce Carolyn Kirksmith, who is the CEO of MycoHab. It's a company that we started together with her and Dr. Andreas Mershon from MIT, and I'll let Carolyn take it from here.
Hi, thanks, Chris. I appreciate that. I'm Carolyn. I'm from South Africa. I'm leading the MycoHab initiative, soon to be CEO, all going well, of MycoHab. But my current day job is I'm the head of strategy and executive at Standard Bank Group, based in Johannesburg, South Africa. So I think being head of strategy and involved in strategy is actually the reason that I'm involved in MycoHab as well. Standard Bank Group is Africa's largest bank. It operates in 21 countries in sub-Saharan Africa. It has a market capitalization of around 18 to 20 billion, depending on what the currency exchange rate is on that day. African currencies are highly volatile. We employ about 48,000 people. The reason I'm raising this is most people look at us and ask, why on earth is a bank being involved in mushroom mycelium and building materials and now blockchain? What has this all got to do with banking, but what has this all got to do together? Hopefully by the end of this, we'll give you just a taste of how this all links up and why it's so exciting for Africa. So before I even go forward, I just wanted to say a huge big thank you to the Biocene conference and to NASA Glenn and to Ohio Aerospace Institute, because it was at this exact conference, at this podium, that Dr. Mershon from MIT and Chris first met about 4 years ago. It was a couple of months after that I met Dr. Mershon at Andreas at MIT. We do a lot of work with MIT. We have a deep relationship with them. And I got to see this technology and was being explained to me as amazing, cool technology they're developing for NASA's Mars initiative. And I had to ask one question, like, who's doing this on Earth? This is mind-blowing. And as soon as you ask a question like that, he looks at me and nods and smiles. And I'm thinking, oh, my goodness, someone get this blonde banker out my office. I don't know why I'm speaking to you. And so when I explained to him, we might be the biggest bank in Africa, but we have a fundamental challenge. We are dealing with significant issues and challenges in banking. All banks are across the world. We're rife for disruption by the digital revolution that's rapidly taking place at an exponential rate. In addition, we are the biggest bank on the second largest continent on Earth, Africa. Africa is often spoken of as if it's a country. In actual fact, it's a continent that's comprised of 54 separate countries. These are independent, unique, and very different countries. Africa is poor. So there's no other way to say that. Africa is poor. They have a lot of systemic and underlying big challenges that we have to deal with. Challenges is one thing we're not short of on the continent. So unemployment, homelessness, just dire levels of hunger and malnutrition, and bad education systems. So a lot of illiterate, uneducated populations. I'm not used to standing on this board, so apologies. And then we're sitting as a bank saying, we've got to think differently. A bank is only a bank. A commercial bank is only a commercial banking operation if it has customers to serve. So if a lot of people are losing their jobs and losing their income and their revenue in the digital disruption or in the digital era, and are battling, particularly in continents like South Africa or continents like Africa, to find alternative employment, who are we going to bank? Who are our customers going to be? This holds true for corporations as well. So when you take a step back from that, then you ask the question, who are we going to bank in 2 to 5 to 10 years' time? And instead of trying to answer that question from a traditional where we are to looking forward approach, we actually started asking the questions like, how can we be part of a solution or part of the team or a group that can find a solution or help us grow the customer base of the future? How do we invest in society, invest in the environment such that we can secure a customer base of the future? So it does sound extreme, it does sound bizarre. And Standard Bank Group's board, on hearing this technology, having the opportunity to see it firsthand, and our very senior executive team who were at MIT at that stage, we very quickly went from question into a full-blown initiative. So Standard Bank sponsoring this work. Our pilot initiative is in Namibia, Windhoek, Namibia. We effectively started operations physically in 2020. That was when we started mushroom cultivation. What you see up here is Chris Maurer redhouse's design for the first mycelium, human habitable mycelium building that we're aware of today. So we started with mushroom cultivation in 2020 with the view to turn, once we'd harvested the mushrooms that are growing, that just gives you a view of our site as it is today. We're using shipping containers, so quick, fast, how can we iterate, quickly move and expand as quickly as possible? At that stage, the best way to do this was shipping containers. We are leveraging, or as Chris mentioned, there's a significant ecological disaster that's taking place in Namibia. It's been a disaster that's been coming for over 100 years. Namibia has an encroacher bush problem. It's an indigenized bush that's taken over the entire country. So I'm talking the whole area of the country. Namibia relies on its grasslands to feed both wild animals, game, that are critical for tourism, as well as a huge cattle industry. They are a dry, arid country, effectively a desert, so they rely on underground water aquifers. So what these bushes are doing, they're very deep rooting systems and very wide rooting systems. It's rendering these aquifers redundant. There's no water. And it's choking out the grasslands. It's affecting their economy. These bushes are full of thorns. They're incredibly difficult to extract. And once you've taken them out, what do you do with them? Most of the farmers and most of the landowners, stewards, were burning them, so releasing tons of carbon back into the atmosphere. So Namibia was also looking for innovative ways to leverage this bush, to give value to this bush that encourages people to sustainably harvest it, to be able to turn it into useful materials or products or goods. So BioHab, MicroHab offers one opportunity for this. It was radical new technology we were testing. So we started with this encroacher bush to see if the mycelium organism, we're utilizing a white oyster mushroom, would grow on this. And surprisingly, it really loved the encroacher bush. So what we are doing is once we harvest the mushrooms, I'll show you photos of that and come back to this. Sorry. This is mushroom cultivation from the encroacher bush. What you can see toward the end of the screen on the left-hand side is once we harvest those mushrooms, what's left over is a composite material. That's a mycelium composite material. We're turning that into waste. into building material, that waste into building material. Why is this so important? It's because 1 kilogram or 1 pound of encroacher bush, a problem, ecological disaster, plus a bit of spawn and a bit of water, is actually generating 1 kilogram of nutritious food, which in this case are the oyster mushrooms, plus 1 kilogram of building material, and it's enabling us to store about 1.5 kilograms of carbon per brick that we are using. This is an exciting formula. In addition to that, this mycelium composite material has 4 properties that blew us away, which is one of the reasons Standard Bank got quite excited about this. Is it's inherently structural if it is compressed. The second one is it's a very good natural insulation material. It's sound attenuating and very important for low-cost affordable housing, dignified affordable housing, is that it's fire retardant, fire resistant. Most of our homeless populations live in tin shacks known as shanty towns, which are dire, dangerous, and just undignified in every way. And what happens is, as soon as a fire takes place or takes hold in one of these shacks, it spreads like wildfire, literally within minutes, and it can take out that entire shanty town and kill hundreds of people. So for us, building material, the fire retardance, fire extinguishing capability is critical. What's important, having those 4 properties in one material, inherently in one material, is quite interesting because we don't need 5 to 10 different materials to build or grow a house that's dignified and affordable. So why is this exciting? I mean, we're just at the beginning of this. It gives us the opportunity, given the sheer size and scale of the problem with the encroacher bush, is just looking at the opportunity we have detailed on this slide, not only to leverage that bush, turn it into an economic contributor, not an economic disaster, as well as deliver food and building material and other products from that mycelium composite, but then sequester tons of CO2, gives us a unique opportunity to deliver circular value ecosystems that are local. So we're investing in the community, we're investing in jobs, we're investing in the environment locally, not depending on international aid. So it's hopefully growing those opportunities going forward. Once we harvest the material, we press it currently into bricks that you see on your left-hand side. This is actually one of our bricks in Namibia. We've had to go with bricks because that's what local architects and engineers wanted us to do, given that they've never used this material before. And I'm going to hand back to Chris, just take you through some of the numbers. But this is one of our colleagues who is our site manager in Namibia. This is not a scientific test in any stretch of the imagination, but it's such a fun video. People enjoy watching it.
Yeah, this is definitely my favorite part of this job. So that's Pendapala. They're demonstrating an impact resistance to the material. Let me see if I can play it again. Yeah, okay. And then some of the numbers there, the mass is exactly the same as a CMU or a concrete block. The compression strength, we've made materials in our lab in Cleveland that are 2 times the compression strength of concrete. Bending strengths that are way stronger. Obviously, concrete blocks are very brittle material, so they don't have much in bending. But insulation is also another one. So this is a thing that is naturally insulative, and then by the thickness of the material and the self-extinguishing nature of mycelium, becomes a fire-resistant material as well. Some numbers I'll go through quickly. I know we're running out of time. 100 billion tons of building materials are made each year. The global building floor area is expected to double by 2060. So take all the buildings we have now and double it. That's about 230 billion square meters. Current carbon emissions are 34 billion tons. So if we look at the 10% of that being embodied energy, that's 3.4 billion tons embodied carbon. And then so 100 million tons of that would be from transport alone. Let's see, we said 1 million tons of CO2 could be eliminated if we If we were to use locally sourced, 100% locally sourced, that's kind of something. But again, the carbon storage of this is where the real story is. You could look at 1.5 billion tons of CO2 stored in materials if we were talking about just 1% of the building industry's materials being done locally fabricated and having this bio-based project. So I'll quickly, I think we're low on time, so I'm just going to mention that we're working with a distributed ledger technology, blockchain. I'll offend Justin by saying blockchain, but as a way of using food provenance and quantifying those carbon credits. So it's, one thing to say, okay, very back of envelope, we're talking 100 or 1.5 billion tons of carbon, but let's account for that. So, we're working with the bank, we know how to do accounting, but we want to do it in a different way, but it's carbon accounting. And tomorrow when we do Meet the Expert, our colleague Justin, who is with Hedera, a distributed ledger technology company, is helping us develop these systems that not only do the carbon accounting, but also regeneration of wildlife refuge is going to be part of that, and food provenance. So, the safety of the food and where it comes from, and can you trace that all the way back? If you buy something in a supermarket here in Cleveland, can you trace that all the way back to the farmer in Namibia, and maybe even give him a tip if you want to? We'll see if we can do that. So here's all the fancy graphs from Justin, and I'm not going to explain it. But basically, the main point we wanted to do is provability of that requires mapping the life cycle of the product. So again, we're talking about the carbon storage minus the emissions required to bring that back online is in the form of a building material. That all needs to be done with independent verification sources, and the one mentioned here is the Forest Stewardship Council, and that's all over the world, but they are working already in Namibia with other organizations. And this kind of gets into building NFTs from that, and you guys probably know that that signature non-fungible tokens. We're looking for a good tagline for non-fungible tokens. So if anyone can help us out with that, we want to develop some NFTs for that. But one really important thing about this is, okay, so we have carbon credits that we're trying to get from this, and a lot of folks know that minting or putting things on the distributed ledger technology or on blockchain costs a lot of energy, and so are we throwing this all away by minting an NFT or by tracking these credits on a distributed ledger technology? It's one of the reasons we're working with Hedera on this. You can see the watts per hour per transaction required for this, and if you do the scale factor from 0.04 to close to 4 million, you can see that there's a huge difference in the amount of energy needed for each one of these transactions. So we're looking for green technology when it comes to blockchain. That's one of the main problems with blockchain at this point is the amount of energy needed. And so we'll just kind of leave it there. Thank you, and look for questions, because I know we want to get some time for some Q&A.
I'm curious about the relative cost of making the mushroom block versus the concrete block.
So currently, we kind of joke that it's costing tens of thousands of dollars for every block we make, because it's a research and development project, right? But when you actually look at the cost of materials for doing that, I think we were at something like $15 a brick. Again, mostly because this is R&D, very small scale. We're paying architectural interns and people like that to make these materials. But when you look at the process, you have this cost of creating the mushrooms, and then you have the sale of the mushrooms, and then you have the cost of creating the material. So that chart kind of goes up, and then it goes down through zero, and then back up. So the goal is actually to get this a cost negative product. So if we're growing mushrooms and we're selling those mushrooms, and then we turn that waste into something, then basically it's just the energy cost of converting that waste into a new material. And so that's how we look at powering these humanitarian projects, because we've already made our money on that. We have the goodwill of saying that we are putting the proceeds for things like mushrooms towards humanitarian housing. So that becomes something that we almost do for free. So it's a cost negative material. Ideally, we're not there yet. $15. Yeah.
What are the activities that are going on right here in Cleveland or the Northeast Ohio? I know you mentioned it. Would you mind just going over what are the activities going on here?
I hear you. Where? Okay, there you are. So here in Cleveland, so we have a workshop here in Cleveland that's running concurrently with what they're doing in Namibia. They have the tools and the talent there to make very large blocks. The about a cubic foot, as you saw in that slide. The ones that we make here are very small, but we're doing the R&D here as well. The one that's kind of focused on Cleveland is what do we have a glut of here? We don't have Acacia mellifera bush to use. So what are we using? We're using waste buildings. So we can take construction and demolition waste. There are thousands of buildings that the Cuyahoga County Land Bank tears down every year. Imagine trying to divert that from landfill, remediate the stuff that's in that, and turn that into building materials as well. So here the process would be more along the lines of making material and remediation rather than making food and material. But it has that co-benefit process where you're doing one service and making the building materials. Three services really, because you're talking about diverting waste, you're remediating, and then you're making building material, new materials to build with. So that's called the biocycler.
We have about 3 questions. So Carolyn, you want to take the first one?
Yes.
Are you currently convincing banks, especially internationally, to invest in this model?
Yeah, that's a very good question. Sorry, I'm not good at balancing on this thing here. So it's a very good question. We're being contacted by a lot of banks who now very interested in what we're doing. It not only transforms the mortgage market, but it also makes real use cases of distributed ledger technology, carbon accounting, carbon sequestration, makes it real, bundling it together with humanitarian process. So we are starting to work with a lot of international banks who also operate in Africa. So yeah, we're starting to. There's a lot more to do. Thanks.
And then Chris, we have a couple of questions I think are meant for you. So do the bricks have to be solid?
Yes, so you might be reacting to the fact that the concrete blocks are cored. They have holes in them, and the blocks that we make are solid. The reason CMUs or concrete blocks they aren't solid is because they would be much too heavy if they were, and because that material is something that's a carbon emitter. So when we're looking at our material, it's more beneficial that it's solid actually, because we're packing more carbon into the material. But yes, they don't need to be solid, but there's actually a benefit of making those having more volume in our product as opposed to concrete blocks. So yeah, but same mass roughly as a concrete block.
And then one last one for you, Chris. Where do you foresee potential roadblocks on implementing these bricks at scale?
How many should I go through? 5. Yeah. It is a naturally biodegradable material. So this is a material that would have to be detailed very well to protect it from things like other fungal competitors, from vermin, things like that want to attack that. So it has to be detailed in the same way that you would detail softwood in construction. So here in Cleveland, we build a lot with 2x4 construction, 2x6 construction. Same thing. It's a material that would degrade over time if it was exposed to the elements. So you have to detail that as an architect in a way that protects it. What we're doing in Namibia is we're rendering all the material. We're putting a lime plaster on the outside of that, and that's a natural vermin repellent and a waterproofing agent that's used to kind of protect the material. There are all of these other material characterization tests that need to be done for these materials. So that's a very long process, but that's kind of how we look to prove the safety to folks that may be skeptical. So kind of an uphill climb to convince building departments and everything else that we are building from the waste of mushroom cultivation. And then the third thing is, I purposely said waste of mushroom cultivation. We always have to make clear to folks that we're not using mushrooms to make these materials. We're using the waste of the cultivation of mushrooms to make the materials. So the food is actually a co-resource of this process. We would never turn food into something other than food, because that's its highest and best use. We want to feed people as part of this process. And also convincing people that usually when we get press requests, the first thing they do is start with the title, and they're talk about mushroom houses. They talk about building with mushrooms and et cetera. So that's one of the roadblocks is kind of educating people the difference between mycelium and mushrooms, which are the fruiting body of the organism.
Yeah, you kind of answered my question a little bit, but from a building construction perspective, right here. From a building construction perspective, what is the most difficult test that you're trying to overcome from a safety perspective for this new building material?
I would say consistency is the most hard part of that, because we've made materials that we use that metric of 26 megapascals. We're not averaging that now, so a lot of the materials are much lower, definitely above the line of building safely one-story buildings. So we're not too worried about the safety of it, but it's getting it to optimize the process to a point that we can consistently be at that structural capacity at the same insulation value. So things like that are consistent over time, because the nature of the growth and firstly growing this for food does in some cases have some inconsistency to it in the quality of the material. But that's something that we're working through, and as we scale up, that becomes something that is easier to do, because we'll have automated systems rather than a human touch on every part of the process.
Presumably the bush is part of an ecological cycle where factors of change, climate, browsers, those sorts of things. I'm just wondering, what are the implications? Have you modeled it, simulated? As climate change progresses, what's the prediction for conditions for growing the bush, which might change and affect your supply of your materials?
Thanks. That's a brilliant question. And here I go again. Sorry. And then it's actually one we get asked quite a lot. To just give you an idea of the extent of this challenge that Namibia has is the bush encroachment. When I say it covers the entire country, and Namibia is quite a large country. So there's 46 million hectares of bush that they believe have to be dealt with and sustainably cleared. We can only leverage that's sustainably cleared. Given those deep rooting systems, you never actually pull the roots out totally. So these bushes grow back within a year to 18 months. They start growing back again. So this is a perpetual cycle. We're working with an organization called Carbon Capital and another one called Namibia Biomass Industry Group. And this is a core focus of theirs, is how do they deal with this and turn it into an economic powerhouse, not an economic drag. They estimate that with all the potential applications or use cases of this biomass today, including green power, et cetera, instead of using coal, use this bush, pellets from this bush, they estimate they've got more than 100 years worth just from the bush that they have available today. So from our modeling and understanding, working with these organizations, we don't believe we're going to run out of that bush anytime soon. So.
And some of the causes for that, shout out to Billy, are the changes in migration over time. There used to be elephants and all kinds of wild animals that trampled the bush, and so that's one of the main reasons is when the ranching industry started taking over and sectioning off land and putting up fences. That became the problem that started that, and the current trend of the bush encroaching is leading towards a desertification of the area. So getting rid of this is a huge priority for Namibia, and just this glut of material. What can we do with it? And trying to turn that into an opportunity, which we try and turn into several opportunities at the same time.
Thanks so much to Chris and Carolyn for such a fascinating presentation.
Thank you.